All right, welcome back. So now we will slowly progress towards generative adversarial networks, and then in the second part of the session, I'll introduce you some concepts around diffusion models. And the goal is that we understand some, or at least we get the understanding of how the GANs work compared to VAEs, variational autoencoders. And tomorrow morning, I've been told that you have a session where we'll be talking about the practical applications of GAN. So I'll give you some examples, but then it will be a more detailed discussion in the morning tomorrow. Good. First, I'll just try to motivate you from from the aspects of some examples, and then I take the very first example, which was the first work that was done in 2014, which came out regarding the face recognition, or generally say, let's say, generative adversarial network. And here you see a very small, brief schematic of how the method actually works. So if you all remember, we spoke about this particular aspect, right? Everything that we discussed today in the morning was about latent space. And now we start from that latent space, and then we proceed further down, and then try to see how we can make use of the discriminator and the generator network. So what does this GAN usually consist of? It consists of the generator network here, and the generator network takes whatever the learned representation space you have, that is called the embedding space, right? So again, just to recall, embedding space is nothing but some space that you have created using a network which can extract the features. And from this one, what you're trying to do is that you're trying to look for another aspect here. Maybe I should just zoom it up. Okay, so you have your generator here. The generator takes some noise into the account, and then it starts creating a new sample. And then the moment the new sample comes in, you have some real samples on the right side up here, and then they are compared against this discriminator. So the lesser the difference between the real and the generated content, then you are accepting it, right? So the whole idea is that you want to push the distribution from, let's forget about distribution. You want to push the generated samples as close to the real samples. Simple, okay? So here is some simple examples how you can use it in face recognition, right? So you have a trained network, and then you extract the features from the network, and then you try to create the face recognition, face images here. As you can see from the left side here, right? So if you take very early, when the network is not fully trained, you get the images that are like this. Looks like face, but not completely. And then you continue improving the model further. And at some point of time, it starts looking better and better. And the last row here, the last column here, actually shows you all the images in the final stage. So this is just to give you an indication that how it can work. And then taking it and relating it to our own work, we wanted to, which we'll talk about it in detail tomorrow. But here is another idea where we use this GAN approach to create new samples. And the idea here is that if I have two people, let's say the subject number 1, Maipal, and here is this second person, let's say Naveen, and then we want to combine both of them, and then we can make use of this GAN network and then create this new image. Okay. So this is typically called as morphing attacks. We'll talk about it later on when we come to that particular session. But the idea here is very simple, right? We are transferring the style and the characteristics of one image to the other image. Now, in your own fields, I think some of you are working in spectral imaging, some of you are working in hyperspectral imaging, geosensing, some of you might be working in medical imaging. So there we could also use the similar ideas, right? So we could take the images from, let's say, from X-ray machine from Philips, and then try to create the same images when it is captured from Siemens, right? So the idea remains the same, right? And then if you want to go even a bit further down, what you can also look at is that you can also use similar architectures. That was the follow-up work of the previous slide that I showed you. And here again, the idea is the same, right? So I have one particular image here of person A and another image of person B. And then I simply extract the latent feature of this one, a latent feature of this one, and then I combine them here. And once I combine them, I can simply reconstruct the image again to get this nice output, which is here. And in between these two things, we also notice there are some challenges that you will encounter, right? Maybe the identity information of the person is not correct. Maybe the appearance of the person is not correct. And then you have to do some simple mathematical tricks where in this case we introduced a new loss which was trying to capture the discriminative information between two different subjects and then keep them in the final image. Okay, so the idea is we have a generator network and we have a discriminator network and we try to make use of that. And why do we say that these are slightly better than VAE in this specific case, right? So if you look at the images here, so the image number 1 and the image number n, which is here, these two images are combined. So when I combine using different approaches, you can see that the approach that was used using GAN, they are very good quality. Now this is one example, right? After this, we also did a couple of other works, but then this is mainly to give you an indication about what other kind of applications you can think of. Now you can also think of transferring just the style, right? So you have a style of, let's say, a famous celebrity, and then you want to transfer that particular filters to your own image. You could do it with GAN, right? So it's not only just about synthesis, but it's also about multiple other applications. Okay, so now going back to the idea of GAN, how do we go from anything that was in VAE domain to GAN networks or a GAN domain? So the architecture somehow looks like this. So you have, let's forget about the fact that we have this noise. For the moment, you can start from here. You have a generator, and then there is a generated output X, and then there is a discriminator which gets the sample X, and now you have to compare the generated X versus this X. Right? So you are trusting your network to generate something. It generates you some image, and then the discriminator tries to say how different these images are. Now, as soon as we do that, it's again nothing but a simple distribution problem, right? So there is a distribution of this particular block, there is a distribution of that particular block, and then we want to minimize the distance between them. So going back to the information theory, we'll come back to this formula here, but again, we can break it down into two simple components there, right? So we'll talk about that, how we come to that formula in a very short moment. But just remember, the whole objective of this case is to play this min-max game. So what should be the min? The generated sample and the real sample, that should be min. And the images that we are generating from the latent space itself should be max, right? So it's a two-player game. And then where are they used as of today? So today they are used for synthesis of images. And today we had a discussion in the afternoon with Ravinder. I don't know if he's around. He was talking about this problem of resolution. So you very often you have these images which are of low resolution, right? And then you want to improve the resolution of those images. This is very common in, if you look at the images from this old generation smartphones, you would get the face image which is not 1 megapixel, right? So you want to improve the resolution. And then you have the second one, which is also in the medical applications. We have this 1.5 Tesla machines right now, MRI machines. For those of you who are working on that, the quality of those images are not extremely high, right? But if you are a patient in the hospital, you want to see that the image is of very high quality. What do? Either you can go back and then purchase a new machine, or you can try to use these kind of approaches to improve the quality of the image. Okay. And then the third aspect I told you already about the style transfer. And one of the other applications of GAN is also in data augmentation. What do I mean by data augmentation? So if I have to train a very good network, I need to have millions of samples, right? So every time I train any network, I need to have 100 cat images are not sufficient. So I would need millions of cat images. So what do? I can go to every single house and capture the cat images, probably easy. But if I have to do the same thing for medical applications, it's impossible, right? So what do we do in this case is that we have some data, some base data. Using the base data, we try to create the variations of them, right? So as soon as we create the variations of them, then now it is noisy, which means that I can use it for the training. So it's not only for the synthesis part, but it also can be used for training better networks. And in terms of industry, industry has been quite proactive in this aspect. So they have been using this in style GAN, which I showed you in the first part, the first slide, and I also will touch upon that again in later on aspects. And then for those of you who are actually using Adobe Photoshop, you might have seen that there is a new functionality that has come up where you can filter, where you can post-process the image with simple filters. And in the backdrop of that, it's the GAN networks that are working. DeepMind used it for image generation. So you could go in and then type in any particular keyword, any description, and then you would get a nice new image. And then in the fashion industry, it's also been used for virtual try-on. So for many of us who do not want to go to the shopping mall and spend half a day for trying on new dresses, new clothes, it's a nice application, right? So you can just imagine yourself how you would look by putting on those clothes in a virtual mode. Yeah. So there are a number of applications why we should look at this GAN architecture. But then if you break down the math a bit, let's go skip this one. Let's skip probably this one. Yeah, maybe here. Okay. So here we start with something called as noise vector. Why do we call it as noise vector? Because there is some embeddings that we have extracted already from the discriminative network. And from there, we add some noise, some subtle noise into the latent space, and then we try to generate new images out of it. So every time there is a new image coming, there is this discriminator which will say it's real or fake. In our context, real or fake actually means how realistic is the image to the actual image that we are providing. It's not the real and fake when we talk about deep fakes, right? So it's a slightly different term. And then now you go to the specific objective here. Now you can try to break it down a bit. And when we break this down, we can see that there are two components here. The first one is the E of x, the expectation of x, for the P of data, the probability of data x. And then we try to see the distribution there. And along with that, we also look at the latent space. So we have the reconstructed data and the data from the latent space. So how close they are. And now this is again the expectation problem. So for those of you, if you are interested, we could go and derive the math. But if you do not want to do that, we can simply assume at this point of time that there are two components in this loss. And then the only goal of the discriminator is to maximize the probability of correct classification, while the generator has the function of minimizing the probability of that the discriminator actually detects it as fake. So every time the discriminator says that, okay, I discovered that this image is not looking very realistic, so I go back to the generator, I change some parameters, update the parameters, and then generate new image, right? So it's like a continuous game. So as long as you're not satisfied, you continue the training, which leads us to the training, something like this. So there is an update for generator, and then every time the generator is updated, you look at what is the result, and then you go back and then update the discriminator, right? If the generator is becoming better and better, then the discriminator should also become better, right, to challenge it. So one is generating and the other one is challenging it. So if the challenge becomes more easier, what you do is you increase the level of challenge, right? And then, so the goal of discriminator is to distinguish between real and fake, and generator is trained specifically to fool the discriminator. So that is the only two aspects that we have to think of. And again, as I told, it's like a min-max game, right? It's a two-player game. So one person tries to fool, the other person tries to create better samples. And there has been very popular example that has been used in the world of GAN, which is about this artist, right? Every time you have to recreate some artist, so what you do is that you create a sketch of a particular painting, and then you show it to a museum curator, and the museum curator has a deep knowledge about the art, so he would say, well, this doesn't look like this was the painter, right? Let's say M.F. Hussain. So if you are looking at M.F. Hussain's painting and then you create your own painting, anybody that is knowledgeable with M.F. Hussain's painting, you would say, this doesn't look like it, maybe because the strokes are different, right? the way the sketches are drawn are very different, and then you keep on challenging it. So in a way, you are once informing the generator that I did not like the sample, so recreate it. At the same time, the generator keeps on updating its own knowledge to distinguish between all the kind of samples. Okay, good. So if you just take a toy example, so what happens in this case? So when you're talking about the whatever we're talking about, we are talking about these probabilistic distributions, right? So I have the distribution which is here in this case. So the real data, so that is in the blue mark, and then we have the generated data which is here. Now the subtle difference here is that if you look at the normal distribution, we always assume that mean is 0 and the standard deviation is 1, right? So I got a distribution which looks like this one, the perfect blue distribution. And then because I'm generating it, what I'm going to add is like, let's say in this case I've taken a toy example where I've generated it is 1.5 and 0.8 as the deviation. As soon as I do that, you see that the distribution has shifted. Right? This is a univariate or single variate distribution, and it has shifted. And now the goal is to come back to this distribution. It's very challenging to come to ideal distribution like this, but the closer to this one is the goal. Right? So this gives an example. This gives an idea for you, right? And now you can simply extrapolate this one from univariate distribution to multivariate distribution, which is typically your images, your text, your music, your audio, or it could be even something more complex, multimodal, both image and text, image and audio, and so on. Right? So the bottom line here is that the two distributions should overlap in an ideal world. So in that case, what is the input? The input is nothing but a noise vector, which is z, which is learned representation plus some amount of noise, and then g of z is the output, and then it typically uses fully connected layers or the convolution layers, depending on the architecture that you choose. Most likely, you're going to use a fully connected layer there. And then in the discriminator, there are only two components. Yes, please. So if you have any questions, please stop me.
Generator or discriminator, either I'm using a neural network model inside it or I'm using a convolution model inside it.
Yes, it's typically the common practice is to use the CNNs or any neural networks, but that doesn't stop you from this discriminator network. For the discriminator, you could use something as simple as an SVM classifier. But the only problem is that the results will not be very pleasant. Let's say not pleasant, how do you say? More realistic. It will not be more realistic. So the question is very valid. So do we always need to stick to neural networks or can we use some other models? The goal is, in the case of the first one, it's always neural network because that can capture rich representations. That doesn't stop you from using something very simple, trivial convolution filters.
Suppose I have an image. I do some mathematical calculation, I convert them into features, then I use an SVM in first hand.
You could do that. Yeah. So this is a very difficult path, but you could still do that. So the only thing is that the errors that we are going to get will be much higher in that case. So in this case, the only advantage that works for using a CNNs or deep networks is because it has seen wide variety of data. So
we don't have to identify the features also.
Right. So it's learned automatically. Yes. So that is the only advantage. But you are fully right that you can mix and match anything. You can put any simple classifier, any simple feature extractor in the first part, right? Okay, so we were here, right? So we said that, okay, it typically uses a fully connected layer or convolution layer, but then the point is also that it could be something trivial as handcrafted features. There is no rule saying that you should use this convolution features, but if you use handcrafted features, the amount of processing that you have to do to achieve good results will be much higher. Okay, and then comes the discriminator network. In the discriminator network, you have two inputs. One input, which is a generated sample, and then the second input comes as a real sample, which is a comparison baseline. And from those two, you are going to compute the probability distribution, like the distance between the two probabilities. And then as soon as you get that, you can pass it through a simple binary classifier, which in this case I've just taken it as a sigmoid output, but it could be something even more sophisticated, right? And then, as simple as this looks like, within the training algorithm, you had to take care of number of factors. One is that you should always sample the mini batch of the real data, because if you're going to keep sending the same kind of data all the time, your discriminator is going to be very biased, and it will learn that kind of data, right? So you don't want that to happen. So you need to always make sure that you sample mini batch of data. Okay. Okay.
I have there was a famous case of US prison system now where they have bias towards the black
Yes.
payroll system. US
Yes.
payroll.
Yes. That we will talk about it tomorrow and day after tomorrow. Yeah. Okay. And then the other aspect that you should also consider is that the noise has to be sampled and it has to generate the fake data. And then once you do this, you should update your discriminator using both of them. And then make sure that you update both the generator to fool the discriminator, right? Because you are making one thing better, at the same time you should also make the other thing better, right? And there is also this aspect of bias which was now in the discussion. So the idea is here, if you don't do the sample mini batching, then what is going to happen is that it's going to be very biased towards one specific kind of population. Whether it's, if you're talking about male and female, maybe it's going to be biased towards male. We're talking about people of different demographics, maybe it will be biased towards people with brown skin or people with white skin. Right? We don't want to have that one. So we need to train it equally well. So that's why we do this sampling of mini batches. Okay, and then when it comes to the loss functions, the loss function is also quite straightforward, right? It's really not fancy here. The first part is in the discriminator, which takes care of the data that is coming from g of x, the generated data, and then it's the distribution of generated z is nothing but your latent space. Right? So this part is one part for the discriminator, and this is the real part, and then we want this to be as low as possible. That's why you see the minus term in the case of log. Okay. And then you have the generated part. The generated part is only to create these images of sufficiently high quality, which is the same terms as this one. So if you do the log expansion of this one, right? So they actually would kind of cancel out if you put them together. Okay. Okay, then comes the bigger problem in the case of GANs. So which is also something that we touched upon very lightly in the morning. So we don't want the GAN networks to produce same kind of images again and again, right? So if your image is always coming as the same image of the same person, that's what we call it as mode collapse, right? If you take two, there is a very nice book which I can share it later on, at least the title, and there you can see a very nice example where they take the example of two cities and they tell if they are trying to replicate one city to the other city, and if it is always constantly resulting in one output, then the whole network has failed, which is what we call it as mode collapse. And this is also a very known problem, right? It's not something very new. So you need to always make sure that you have enough amount of training data where both the generator will not produce limited variety of outputs. At the same time, discriminator cannot easily detect the fakes. And what do we do in that case? We do this, take the strategies of mini batch discrimination. Within the batch, we try to diversify the data and then provide the data to generator. And then there are also other variants of GAN, which I'll touch upon one or two different kind of GAN, and they fix this problem. Okay? The base version has this problem, and the advanced versions have somehow removed that problem. Okay, one new architecture in that case is what we call as DC GAN or deep convolution GAN. And now, where does the deep convolution come from? In the last part, I was telling you that it's very common that people use fully connected layers, and the fully connected layers are not really very good, right? So in this case, they use convolution layers, and then this leads to better image quality generation. Maybe I could just show the image here from the textbook. So here you can see the figure, right? So instead of having a fully connected layer, what they are introducing is they are introducing from the data space, they start doing number of convolution operations. Right? It's a deeper network now. So this has some advantages which solves the problems that we had in the previous case. And this is the book that I was referring to, which I can share it later on. Okay, so now if I'm going to go back to the situation of GAN to DC GAN.
If we are using a convolution layer, we must be using a filter.
Yes.
So how do we identify that which filters are to be used, or we generally take any filter and use it?
No, the whole idea of using the convolution networks is that they're learned automatically, right?
Yes.
So you don't design the filters. The convolution filters are learned based on your training data. So you remember we had this, yesterday we started with this 2 cross 2. We said 2 cross 2 and we did the convolution. But this 2 cross 2 will not really capture all the kind of patterns. In the last session when Professor Nain was talking, she also mentioned that there are these subtle differences. Sometimes these are activated, sometimes these are activated. So number of different combinations are activated depending on the results that you're going to get. So what happens is that some of them get selected as the final set of filters. So that's the whole advantage of getting rid of this engineered filters. Okay, in the case of now fully connected, deep convolution GAN, what we are doing is that we are starting with the noise, which is exactly the way we did it in the GAN. And now we are introducing fully connected layer here, which is nothing but the latent representations. And then from here, you start doing the deconvolution, because in this case, if you are doing the convolution, what we should do in the other case, we have to do the deconvolution, right? So to unroll the image back. So we start with the deconvolution 1, 2, 3, whatever the layers you want. And then at this particular point of time, you say, okay, now I have generated a new image. And then use this image to give it to the discriminator so that it can differentiate between this and this. Now, although we made this architectural change, what is interesting is that this formula has not changed. Right? You see that we still have the d of x, we still have the d of z, and then the expectations still remain the same. So nothing else changes except the way we are putting the data to generate the data. Pushing the data to generate the data, and also comparing it with the discriminator. So does it give an idea? Okay. So I don't expect you to understand all the math behind this right away, but I want you to understand the high level concepts, and then when you go back, you can start deriving the mathematical equations behind them. Good. And then in the DC GAN generator itself, you have, I wrote it in the previous case as decon. Actually, decon is nothing but the transpose convolution, right? You have x times a, and the convolution part would be, in this case, it would be x transpose of a, right? So it's just taking the, instead of doing this convolution x times w, what you're going to do is that you're going to do this x transpose w, right? So it's just the way of computing convolutions. Again, for these things, you should really not worry, because there are a lot of new tools that are available, massive amount of openly available code that you can take a look at it. But the key goal is to understand the ideas behind them. Okay, and then you have this batch normalization, because every time you're doing, you need to take care of the batch is completely normalized. And then you have activations, which is ReLU in this case, but it could be something else. And then in the case of the discriminator, you have the convolution layers, again the same thing, and then you have the leaky ReLU activations. And then the important part here is that we are not doing a max pooling, because we are interested in reconstructing the image and then comparing it, right? So there is no max pooling in this case. Good. And then you have, this has solved one problem now, but still there are other problems that are still remaining in this case, right? So what is the other problem? So any problem that we can think of as soon as we talk about these convolutions? Anything that we spoke about yesterday? We all did some exercises. Vanishing gradient problem. It's a problem, right? We are not solved it here. So this is gonna haunt us again and again. So what people have done is that now people have come up with another model which is called as Wasserstein GAN. Okay, so the Wasserstein GAN is also a very popular model. In this case, what they're trying to do is that they're trying to model it using this Earth mover distance, which is nothing but instead of using the original equation that we had, they changed the way the distance is measured. And what exactly is that change? So the objective becomes quite simple. They say, okay, I have two distributions. I only try to maximize the expectation between these two distributions, which is d of x coming from the generator, and then d of g of z, which is coming from the discriminator. So what did we get rid of? We got rid of only one aspect, which anyway we said which would be a cancelling factor. Right? You remember I showed minus log of p of x, and then there was another one which was minus 1 minus p of g of d of x, right? So there were two terms. If I put together both of them, they will cancel out at some point in time, which is exactly what is being done here, right? So in this case, they are looking at the distance is now the distance between two different probability. And now in this case, so the discriminator is still a critic. It's now not called a discriminator anymore, but it's called a critic. And in this particular architecture, there is no sigmoid activation. So as soon as we have no sigmoid activation, what we are going to get is we are going to get a number which is a typical score. In which case, what we call is that we call this as this critic function instead of discriminator, and this critic is going to give you a score which is a real number. Right? So just that the only difference here is that we are not going to get the probability score there. We are rather going to get a single number which we can use further down to update the whole network. For those of you who are even more interested, I can give you some more tips. The tips here are, one of the advantage of this Wasserstein GAN is it enforces this Lipschitz constraint. Those of you who do not know this, don't worry about this. It's nothing but it's addition boundaries. Okay, it's a boundary between classes, boundary between hyperplanes, and so on. Because of this inherent ability of doing that, what we're going to end up in Wasserstein GAN is that it's going to give you this network with greater stability, and the convergence is much faster. So typically in GAN, if you are to train it for 10,000 iterations, in this case in Wasserstein GAN, you don't have to do it for 10,000 iterations. It will be much lower. Give some motivation. And again, there is no guarantee that this would work for your application. You have to look at your data, understand your data, and then try to play with this. Okay, don't take it away. Don't take it as a golden rule to go for Wasserstein GAN just because it's giving you stable performance or faster convergence. And if you just take a simple overview of all these three architectures, now I'm just taking only three, but you can also have a multiple table here. So the overall architecture in this case of in the GAN is it's using KL divergence. In a way, it's also Jensen-Shannon divergence, another version of that, which means that it's going to be unstable. But then if you use Wasserstein GAN, it's using a distance which is based on Earth mover, and then the performance is more stable. And in the case of this GP, it also takes into account the gradient penalty. So this is more advanced version compared to the WGAN. Okay. So again, remember this is like to introduce you to the family of GANs. So then you have an idea of which one to choose when, and then you can select particular architecture. Okay, just to recap everything that we have been talking about, the formula for the loss in this case is nothing but the generative adversarial network. It takes the generator part, discriminator part, but then it uses this JSD. JSD is also very related to the KL divergence, so you can look it up, and because of which it has a vanishing gradient problem, and also its mode collapse is a very inherent problem in this case. And then in the Wasserstein GAN, what they did is they just simply removed the JS divergence and then they introduced Wasserstein distance. And then once they introduce this, the term which we used to call as discriminator now vanishes. It is now replaced with something called as critic, which is exactly the same functionality, but it's called critic. And then it also gives you a score, right? It doesn't give you a sigmoid activation, the probability from the sigmoid activation. And with the gradient penalty, what exactly is happening is this particular part, right? So we were talking about this generated sample from here. Now we could also introduce an interpolated version of this reconstruction and then try to do a critic of that. Right? So I presented you the variant which is much more stable, but the only change in this case is that we are also making use of this interpolated X hat. So this interpolated X part, this one, this is a sample between the real and the generated one. So let's say you are in this space, so you are X, and this is your X hat, which is computed, right? So now you measure the distance between them, and then you say the distance is, let's say, 0.8. So what you're going to do is that you're going to recreate the interpolated sample of this one, X prime, and then next one, X double prime, and then further down. So every time you do this, you expect that this distance becomes lesser, right? So you are in the same line, in the same space, but you are trying to minimize the distance in this case. Right? So that's the advantage in this case. And as you are also taking care of gradient policy, gradient penalty, what you're also doing is that you are avoiding the weight clipping. So you're trying to keep the weights intact. Okay, just to give a demonstration of how all these three things look like. So if you're taking the GAN, so you see that the training instability is shown here, right? This for a toy example. You see that the network goes very low and then it starts fluctuating up again. And then all the way even here, if you're stopping somewhere at this particular point, epoch number 60, you're very close to lowest error. But then in next epoch, it shoots up again. So this instability is not good for any network. However, if you take the WGAN, Wasserstein GAN, it's relatively stable than this. Right now you see that it's more flatter, although you have higher amount of error in this case, it's still flat. You are able to trust the network more. And then if you take the gradient penalty, now you see that it's even more stable. It's not fluctuating too much, and at some point in time, it also starts becoming stable here. So you can continue the iterations. Here I've shown it only for 100, but if you continue the graph even further, you can see at some point in time all of them become more stable. Okay. Good. Maybe this I can skip because I already spoke about the distribution of different point clouds or different points in the latent space. But what is important in this case is that yesterday we spoke about this metrics such as DET, ROC, and so on. But in the case of generator adversarial networks, what we are doing is that we are trying to measure inception score, which is another metric. And then we also use FID, which is quite relevant for us. Why do we have to use the FID? Because every time we are generating a new sample, we want it to look as realistic as possible. Right? So if you are measuring simply the mean square error, it will not capture the whole properties of the images. Let's give an idea. Okay, and then along with that, you should not ignore the other aspects such as precision and recall, which are going to be inherently there in the network. So you have those two, and then along with that, you introduce these two additional metrics. Okay, and then just to recall again some small tips, try to use batch normalization all the time, try to avoid the sparse gradients, and then also always monitor your loss curve as you do with any other neural network. And some common pitfalls are the mode collapse, which we spoke about, and then it's also the problem of vanishing gradients. As long as we are talking about neural networks, this is going to be there. So you have to come up with strategies to deal with that, and then try to make a discriminator which is not overfitting. Right? If all the samples are getting discriminated by the discriminator, maybe the discriminator is extremely good for that particular kind of data, right? Which will lead to unintended consequences later on. Okay, good. Then I'll not spend time on this one, but then I'll spend some time on some popular models. In the very beginning slide, I showed you the picture of first work on GAN, which was in 2014. And then is the other work, which is another milestone work, which is in 2019. This was also a very nice architecture. And here you can see that, I'll not get into the details of architecture, but you can see that it can generate very high quality images now. So in the first one, the very first slide I showed you some images which were maybe 30 by 30 pixels, which look like face, right? But in this case now you see suddenly you are able to generate images of sufficiently high quality, which is good for any application. And here, if you are further curious about the architecture, you can see that there are some subtle engineering aspects that come in here. In the case of traditional aspects, you have this latent, normalized, fully connected, and then a couple of other blocks repeated number of times. But in the case of style-based generator, what they're trying to do is that they take the normalized version from there, and then there is a mapping network here, right, where they're trying to map each of them into different aspects. And of course, there is significant contribution of what is called as ADI, or how do you say that? Adaptive instance normalization, which is also playing a big role. So this also relates back to the aspects of normalization that we are talking about. But then here is also another very interesting aspect. One thing is that your mapping from latent space is very, very critical. And the second thing is that there is this trick called as truncation trick. So in the case of VAEs, we had this reparameterization trick. In the case of GANs, we have this truncation trick, which says that if you have the truncation factor of 0.7, then the results are much better. Below that, they're bad. Above that, they're bad. For some magical reason, 0.7 seems to be working really good. Okay. And then that would also mean that in this architecture, they introduce all these subtle changes that enforce them to have very high fresher interception distance score, which means if I wanted to generate the image of Professor Nain again in the second round, the image would be much more similar to the actual image, right? So this score should be as high as possible. But then if that was of course one of the milestone work, but then if you take a closer look at those images, the task of the discriminator becomes much easier. Why does it become much easier? If you look at all these images that are generated, look at the areas that are marked in the red circle. There is a subtle signature of the image, right? Every time the image is generated from this network, you start seeing some spots, and these spots typically appear at the areas where there are edges. In the case of this particular lady, there is an artifact on the top of the head. In the case of the horse, there is an artifact on the top right of the image. And if your discriminator is carefully designed, it can also look into these images, right? These artifacts. As soon as it does it, then your system is actually not very generalizable. Then came the second work from the same group who identified this problem. And what they did is they made some very small changes. Now the small changes actually are coming from the architecture here. If you pay very close attention to this, the only thing that is changing here is that this remains the same. The B, which was going here, is now course with mathematical foundation behind that, and that led to much better results. So the current day popular models are StyleGAN 2 models, which are generating very realistic images. Okay, good. And then while we're talking about this particular aspect, we should also talk a bit about one other popular model, which is called as FSGAN. In the case of FSGAN, it is there is this common problem, right? If I'm trying to generate number of face images, it tend to become very subject specific. And what they wanted to do here was that they wanted to transfer the style from one person to another person, from this face image to this style, or vice versa. So what do you look at that? When you look at that image, you see that the hairstyle is different, the facial characteristics are different, and the background is different, and so on. So what they did in this work is that they introduced this this idea of GAN by having two different generators. For instance, the generator number 1, this is for GR, and the generator number 2, this is for the style, GS, and then they combine these two for the generator number 3, and then that could generate multiple images. Now you asked me about the question about the interpolation space, right? So where we took over this one. So isn't this very similar to the interpolation space here? So we're in the same image space, but the images are slightly different between each other. Right? And then once you have that one, so then you can give it to the other unit, which actually creates the blending. But the idea here is that the GAN architecture comes into the picture in the much earlier part of the block. Okay? So to give you an example of how GAN can actually be used in the real world. Now, I was always telling you that the loss function is quite simple in almost all the cases of GAN, but what actually is reality is this one. In the case of FSGAN, the moment you have more complex terms, more complex parameters coming into the picture, the loss also becomes more complex, right? Because you have to take care of each independent part. And in this case, if you look at the generator loss, it's not just P of X anymore, or sorry, P of Z anymore, but it's a combination of a constructed image, actual image, and then there is also the second parameter, third parameter, and the fourth. So there is a number of parameters that are coming into picture. So the more complex your network becomes, the more complex the loss also becomes.
You have designed this loss function. This is not the standard loss function which is available, right?
The loss itself is standard. For instance, here, right? If you look at that, there is a loss function which measures the difference between the color channels. You have C, H, and W, which is channel height and width. Across all the channels height and width, you are measuring the single the L1 distance between them, like the simple distance, right? And that serves one purpose, but that doesn't serve the whole purpose. So now what you do, you introduce pixel-wise loss. How many pixels are faithfully reproduced? And then you have the second one, which is now at this point of time, you have the pixel loss and the perceptual loss. I can put them together, then I can create a new loss. Then I'm sure that the regions are consistent and the pixels are consistent, right? And from there, I can make use of the old loss, which is nothing but the generative discriminator loss, which remains as it is, right? There is no change in this case. But now that you have multiple discriminators, so all the discriminators are taken into account, 1 to n, right? And then the base formula itself remains the same. Right? So all I'm doing is that I take care of my base purpose, and then I also add other parameters such that my goal is fulfilled. So in this case, the goal was to make sure that the style gets transferred. And here you see that there is also another aspect, right? This is a specific case of facial reenactment. In the case of reenactment, they also wanted to make sure that the lips are in the same region and they are not moved up or down compared to the subject which is being targeted. Okay, I think we could stop at this point, yeah. But before I stop, I just wanted to reiterate one more aspect, one more time. Remember that GANs are very powerful for generation, but then there are some subtle problems. And to address these problems, we go from normal GANs to DC GANs, which makes use of transpose convolutions, and it has a deeper convolution layers. And then even better one in terms of training stability is this WGAN or Wasserstein GAN, which makes use of the Earth mover distance. Okay, there is this generations that have followed from 1 to second. And then if you want to do a further reading, so these are like the 3 works that I could recommend. So one is the original work from Goodfellow and et al. And the second one is the Radford et al., which is on DC GAN. And the third one is Arjovsky, which is on Wasserstein GAN. Okay, I think I can stop here and take any questions before I go to the next session on introduction to diffusion models, so that you have an understanding of diffusion models for the discussions tomorrow morning.
Can you actually highlight how these concepts can be used in the software design? When you're implementing this, is it taking a lot of time?
For the
Time
implementation.
complexity and space complexity.
Okay, so there are 2 aspects, right?